All right, so as I'm thinking this through, this area of this sector, are you with me that a sector is a fraction of a circle? So it is going to be a fraction times pi r squared. Is everybody with me so far? Okay. So something times pi times the radius squared. Okay? And then what fraction of the circle? Well, so like if I think about this in degrees, if this was say 60 degrees, what fraction of the circle would it be? 1/6. How are you getting 1/6? But you're doing it the other way around, right? You're doing the degrees over 360. Is everybody with me? So it's, which is really just the theta over one revolution, or one time all the way around, right? So it would be theta over 2 pi. And so now the pi's would cancel, so I could write that a little bit more simply. I would have 1/2, I would have theta, and then I would have my radius squared. And that would get me to the area of my circle pretty darn quickly. Is everybody comfortable with that? Okay, so here's what happens when I'm doing that here. Now my theta is a sum of a bunch of itty-bitty microscopic thetas. So the theta part, the sum of microscopic thetas would be an integral d theta, where from some set of boundaries, and those, so now those boundaries are different angles, right? So they're going to be different theta values on my function. Okay, I'm going to have the 1/2 out front, and now my radius isn't just always the same number; it is a function of the angle. So my radius will be r of theta, the quantity squared. And so, like, you're going to be given the r of theta, because I can't ask you to find the area of a curve without giving you the curve. So really, what's the hard part going to be? Finding whatever your bounds are going to be, or sometimes, as you're going to see on the next page, sometimes what we're going to have to do is break it up into several integrals. Is everybody okay?
Yeah, wait, so where did the data go?
It's the integral.
Okay.
Right? Because it's like I'm adding this angle plus this angle plus this angle plus this angle, right?
Yeah.
So it's the sum of it's a sum of microscopic partitions. That's what integrals end up being, right? Is a sum of itty bitty infinitesimally differentially small somethings. That's what integrals are. Everybody good? Mm-hmm. Okay, so let's look at this. So find the area of one petal of the rose curve 3 cosine 3 theta. Okay, so first of all, we can start to get a feel for, and this is why we did, like, honestly, finding these bounds is why we did the deep dive on the graphing that we did yesterday. Okay, so 3 cosine 3 theta, and I hit graph. Now, with the rose curves, y'all, it can be really hard to see. Like, I can see it goes from, like, here to here to here. But, like, this gets kind of hard to see what is the angle here, right? Because I could look at this direction. I could say that angle is negative pi over 6. Or negative pi over, or I could, not negative pi over 6, 7 pi over 6, or 4 pi over 3 or something. But it's really hard to tell. Okay? So, are you guys with me that each petal is essentially being bounded by where the radius is equal to 0? Like, to travel, like, this one technically starts here, it goes around, and then we do this, right? So really, to find the bounds of this petal, I could just look for where does this, for what values of theta would make the radius equal to 0. The bounds of a petal are what make the radius equal to 0. Is everybody good? Okay, so Cool. So let's go ahead and say, well, under what circumstances, for what values of theta do I get a radius of 0? No, but you're close. Okay, so certainly, can we just ignore this 3, right? Because that 3 is never going to equal 0. All right, so math, if I asked you for what values does cosine equal 0, you would say pi over 2, 3 pi over 2, 5 pi over 2, all the odd pi's over 2. Right? So what equals 0 is not theta. 3 theta is equal to pi over 2, 3 pi over 2. The angle of which you are taking the cosine. And I mean, you guys, I can do a doop, doop, doop. So for which values of theta that I'm plugging into my function, do I go back to 0? What I have to do is divide all of those by 3, or multiply by 1/3, however you want to do it. So now all of a sudden, theta would equal pi over 6, or 3 pi over 6, or 5 pi over 6, or, 7 pi over 6, etc., etc., etc. So let's think this through. This is 0, right? Knowing these numbers now, you ready? 0 to pi over 6 to pi over 2, because that's what 3 pi over 6 would work to, yeah? To 5 pi over 6 to 7 pi over 6, etc. To 7 pi over 6 is what's happening there. We getting a good gist? All right, so from here to here, so in between each of these is one pedal. And then in between these two is one pedal, et cetera, et cetera, et cetera. Okay? So if I'm trying to find the area of the pedal, I do 1/2 the integral. So I can choose. I can do if I wanted to, I could have made my lower pi over 2 to 5 pi over 6. I could do from 5 pi over 6 to 7 pi over 6. Each of the pedals has the same area because there's like this whole thing called symmetry. And if I asked you to find 2 pedals, just find one and double it. If I asked you to find all of them, find 1 and multiply it by 3. Everybody good? My cheat sheet's somewhere away. So what's the answer? What did you guys get? 2.356 sounds very reasonable to me. Is this bad? Okay, you guys remember yesterday when we took that deep dive into r equals 1 minus 2 sine theta? It was a beautiful curve, yeah. Here's what I need to do. Look, super careful. All right. Find the area of the region between the inner loops and the outer loops of 1 minus 2 sine theta. Oh, man. Everybody good? So, as we think this through, I'm going around my unit circle. I'm starting at theta equals 0, yeah? So in some respects, we're kind of doing this radius plus this one, plus this one, plus this one, right? And then as I kept going though, like this area is like if I go all the way around, right? And then this area. And it's like, if I go all the way around, I'm kind of like covering up that area. Is everybody with me? Man, this is really weird. And if we go back, because let's start with kind of like that outer loop. Rather than think of it as this, and then stop, and then this, and then this, right? Because that would require two separate integrals. 0 to pi over 6, and then 5 pi over 6 all the way around. Are you guys with me? I want to think of that as one integral. Are you guys comfortable with that? Okay. So what I'm going to do is let's go ahead and call that. Instead, couldn't we just start at the 5 pi over 6 and keep going? So, but when I do that, I haven't cut out that middle because remember the radius is like all the way through. Does that make sense? Okay. So let's start with that my area for just that part, right, is going to be 1/2 the integral. We're going to do, instead of doing two separate ones, we're going to do 5 pi over 6 to 13 pi over 6. And then my radius is the function squared d theta. Can you guys help me out with what that is? Sure. 8.881. Okay, what would the inner area be? Well, that was from so the inner area. Let's just do it. Yeah. The difference is so the inner area. Those angles were from pi over 6 to 5 pi over 6. I would bet it's smaller than 8.81. And then, so if I really want to find what I would call the donut area, though that it's like a donut with a bite taken out of it. Though that would be a pretty weird shaped mouth to take that bite. I don't think it'd be possible. But you guys we would just do a 8.881 minus 0.5544. And yes, you could write that as one giant thing. That would be fine. Okay. So, so 8.337, does that sound about right?
Yeah.
How are you guys feeling about areas so far?
So far, not bad.
Great. Let's see if I can make you even madder.
It's that little area.
We would like to find the area of the region common to the two regions bounded by r equals -6 cosine of x and r equals 2 minus 2 cosine of x. Oh, I said x, but I mean theta. You guys catch my drift, yeah.
So is that like the little circle-ish part? No.
So it's kind of, I'm going to define it kind of like this. It's this area. You guys can see hopefully why I maybe chose these like different colors, right? So it's actually the combined red and blue area, yeah.
Yeah.
All right, so what do we have from here? So why did I split it up into the two colors? My radius is going from the origin, right? And so it's like I'm going here, like I'm adding in this area, then this area, then this area, then this area. So like at the beginning, so for this little piece right here, the radius is going out to the blue graph, which is the -6 cosine theta, right? And then at that point, the radius is no longer going out to the blue graph. It starts going out to the red graph instead, right? So this is the idea of like we have multiple, that point of intersection is kind of important for us to figure out where we're going. Is everybody good? Okay. So we got a whole bunch of things we got to think through here in terms of what are our bounds. Okay, so as I'm looking at this, the first thing I got to decide is at what angle is this starting? Are you guys with me? Okay, so essentially, again, the blue graph, this is the -6 cosine theta, is in blue, and the red graph is the 2 minus 2 cosine theta. All right, so we're starting at this point, we're starting on the blue graph, which is where -6 cosine 0 is equal to 0, because at this point the radius is equal to 0. So to find our starting component, we're going to start with where does -6 cosine theta equal 0, which is where cosine theta equals 0, which is theta equals pi over 2. So for essentially, my first area that I just had done in black will be 1/2 the integral from pi over 2 to this point of intersection. So the next thing I need to find is what is that point of intersection? Is everybody comfortable with the kind of my thought process here? Okay, how can I figure out where two things intersect? Set them equal to each other because I like exact values. You guys know that. So -6 cosine theta equals 2 minus 2 cosine theta. which I get negative 4 cosine theta equals 2. And from there, I'm pretty comfortable saying that the cosine of theta equals negative 1/2. Where's cosine equal to negative 1/2? Well, so 2 places, actually. 2 pi over 3 and?
Negative.
Or 4 pi over 3.
Or that, yeah.
Hey, guys, looking at these points of intersection, 2 pi over 3 and 4 pi over 3, does that feel good? We comfortable with this? Okay, so theta equals 2 pi over 3 and 4 pi over 3. Okay, so again, that blue area is going to go to 2 pi over 3. And for that one, my radius is the blue graph is the cosine graph. So negative 6 cosine theta squared d theta. I know. All right, then we start adding in the red section, yeah? So I kind of have this shaded weird because really it's more like this, isn't it? That's really what's going on in terms of how that happens. Every good? All right, so for that red section, that would be 1/2 the integral . One half, what would my bounds to that section be? That would be 2 pi over 3 to 4 pi over 3. And that for that section, my radius is the 2 minus 2 cosine theta, the quantity squared d theta. And what would that last section be? That last blue section? Forgot my 1/2.
It'd just be 4 pi over 3 to 2 pi.
To where?
Or wait, now.
Remember, we're going to go back down to this, right?
Right.
3 pi over 2.
Yeah.
Now, you guys, if you want. One of the nice things about polars, before you type this in, one of the nice things about polars is we have symmetry, yes? If you wanted, you could instead do just the top half. And then double it, yeah? So then I'd have 1/2, the integral from the blue area would still be, the first part of this integral would be the same. And the only difference is now this isn't going to go from 2 pi over 3 to 4 pi over 3. I'll only go halfway. To pi, which is the halfway point, right? Okay, and the reason I point this out is you'll notice then also this 2 will cancel with the 1/2, and it's a lot easier to type it in and not make a clerical mistake. And what are we getting? So 10 pi is what that would be. 31. Are we all getting the same thing? I mean, that doesn't sound crazy to me. This is a circle with radius 3, which is 9 pi is 27-ish. 28.8. Oh, yeah, that does feel a little bit big.
Yeah.
15?
Oh, that's like 15. Very possible I typed it wrong.
Did you multiply by 2?
Yeah.
And the 1/2?
Oh, I canceled out the 1. Oh,
Wait.
that's what I forgot. to-
Okay. So that would make a ton of sense, right? Like you got half as much. So 15.
There we go.
We feeling okay? Did I pass out new homework to you guys yesterday?
No.
Did I make the copies of the new homework to pass out to you guys?
I know you gave one to Lucas.
I did because I printed it. I don't know that I ever ran the copies of your homework, y'all. So we'll talk about this with a little bit more detail tomorrow. I kind of screwed up. I mean, not really. Yeah, I didn't run the copies yet. I will right now. I kind of screwed up in that last year, all of the polars were split up over to 2 quizzes, and I didn't do that this year. But I didn't change your homework, so like both of these homeworks will be on the next quiz. Will be on Friday's quiz. I'm going to redo. I got to think through is one period. You might be taking the quiz Thursday and Friday next week, not just.
One period.
Yeah.
Okay.
But theoretically, we'll finish the arc length stuff tomorrow. You'll have Monday block day to review stuff, like,
Yeah.
and then I have your test over this scheduled for the following week, block day.
Block day. So Wednesday.
Yeah.
So next week it would be.
Next week should be,
Monday, Wednesday, quiz Thursday, Friday.
and then,
And review Monday, test Wednesday.
yes.
Okay.
But if you guys, like, I would listen to, and honestly, I think it would make more sense, review Monday, which will be a block day. Or, like, no. Monday, we have weird blocks next week.
Oh, we do?
Mm-hmm. So I'm leaning towards review during a block day Monday, take the quiz Wednesday, Thursday, review Friday, Monday, and then take the test. So you have more review days built in where you've taken the quiz. Like,
Yeah, that's
that,
fine.
I think that makes more sense. And then that way we're putting you in a good position. If you guys are comfortable with me bumping that quiz up, I think you have more than enough time, being that like arc length is tomorrow, and then you guys will be ready. Like, I think that's what actually makes the most sense if you guys catch my drift. And then